Okay, well, yeah. So thank you, Lucian, for the invitation to come and speak to you this afternoon. Well, for me, it's this afternoon. In the morning in the in the US. So I'm going to talk about a range of research topics that are ongoing in my group, with a focus on crystal structure prediction or structure prediction in general. And I'm going to talk about topics that have come up in the process of that area of research. So, oh, yeah, okay, so. Structure prediction is something that I got interested in actually right from the very good beginning of my PhD times. So when I started my PhD, it was in the early days of the plane wave DFT craze, I would say. So codes like CASTEP and VASP were just being developed at that point. And my PhD supervisor was Professor Mike Payne, who was the originator of the CASTEP plane wave DFT code. And when I started my PhD, he felt, and this is probably maybe a symptom or a property of PhD supervisors the world over, he felt that he'd kind of done everything. It was all sorted out, and all I had to do is push a few buttons and I'd get some nice results. So he said, well, here's my review article on the topic, and you can get the code from this other PhD student, and you can calculate anything with CASTEP. And so as in some sense, wonderfully naive PhD student, my first thought was that I would like to calculate diamond, carbon diamond. And in my mind, because I didn't know anything very much about condensed matter physics at that point, calculating diamond would mean I would tell the computer program carbon, and it would come back with the diamond structure. This to me seemed like what calculating diamond would be about, and then other things would follow from that. Little did I know that that was kind of heresy at the time. This is not what was done in condensed matter theory. Largely, you would take a structure that was known from experiment, almost a given Hamiltonian, and then you would explore the properties of that given Hamiltonian, not discover the Hamiltonian in the first place. So actually, I did try with this early version of CASTEP to calculate diamond. I made some input files with randomly placed carbon atoms in those input files, and I compiled up the code and I set it running. But in those days, doing even a single calculation was rather expensive, or even on very bespoke sort of workstation machines that we got to work on. High performance computing was less accessible. And the result of those calculations was an almighty mess. I didn't find diamond. I just found that the calculation moved the atoms around for a little while, and they didn't look any more sensible than they were when we started out. So I took the line then that my PhD supervisor maybe hadn't been completely straight with me, and it didn't calculate everything. And two, that if I really wanted to make progress, I was going to have to sort of get much closer to experiment. And so I spent the early period of my career working on theoretical spectroscopy. And so this was using plane wave pseudopotential methods to predict spectra for given arrangements of atoms. And I started with core level spectroscopy in electron energy loss spectroscopy, and then moved on to nuclear magnetic resonance spectroscopy. And these have both turned out to be very useful tools that are routinely used now by experimentalists as part of their analysis of their experimental results. So it's very common now for experimental groups to also have access to plane wave DFT codes that they run simulations using alongside their experiments. But actually, as time goes on, I kept being drawn back to this issue of not being able to compute the arrangements of atoms, because if you think about it, even if you've completely nailed theoretical spectroscopy and for a given arrangement of atoms, you can perfectly match the experiment that had been performed. Those results are only as good as the model that you put into the calculation, the arrangements of atoms. And if you only are putting in known arrangements of atoms, actually the prospects for discovery are quite small. And so if you really want to get into a loop where you're combining computation with experiment to discover new materials, you need a way to computationally suggest new materials. So this structure prediction question just came back again. And so I started working on that more intensively, initially using sort of graph theoretical methods to try and use that to enumerate structures. But this was a combinatorially challenging approach, and it didn't work. It didn't work out. And then I moved on to the technique that I'm going to talk about now, which is a random structure searching. So essentially stochastically sampling the configurations. So this is this slide here, structure prediction. We're answering the question, what structure will a collection of atoms adopt, and those structures might be crystals, and in fact they're often crystals in solid state physics, but they might be defect structures or defect complexes, or they might be interfaces or grain boundaries. Now, predicting a structure is really a global optimization problem, and structures adopt low energy configurations. So somehow you have to move the atoms around, rearrange the atoms so that they're in as low an energy as possible arrangement. Now, not necessarily the very lowest energy arrangement, because metastable phases are absolutely critical to biology, technology, materials science. It's not always the ground state that we're interested in, but the structures are typically fairly low energy. So they're fairly low on the energy landscape. So I'm using the word energy a lot. So we have to decide where we're going to get those energies from. Now, traditionally, before I started working in crystal structure prediction or structure prediction, the assumption had been that the searching or the exploration of these complex energy landscapes was going to be so computationally expensive that you couldn't dream of using first principles methods to evaluate those energy landscapes. So pretty much, with one or two exceptions, pretty much structure prediction at that point involved using empirical potentials. So this is what I would call an interpolative method, an empirical based potential based on observations that we've been seen before. Now, as you'll see later on, these interpolative or empirical methods have come back in the context of machine learning or data-driven techniques, and I'm going to emphasize that towards the end of the talk. But at that stage, my naivety that I hadn't really thought that it was a difficult problem at the time, and I was a developer of plane wave DFT methods, so of course I was going to use plane wave and DFT to evaluate the energy landscape. So I tried it, and it turned out to be the good way to do it. And the advantages of the plane wave of a first principles approach was that it would work under pretty much any situation. So this opened up the door to structure prediction under extreme conditions, which I'll talk a little bit about later on as well. So the rules of quantum mechanics work just as well on the surface of the Earth as they do deep down in Jupiter or other large planets. So this gave us, which wouldn't have applied to the empirical potentials that were around at those times. They were simply not designed for the multiple terapascal pressures that you encounter in giant planets. So this is a real advantage of a sort of theory-driven approach. I will talk towards the end where we are in my group almost entirely moving to machine learning, but trying to keep as much of this theory-driven or first principles nature of the energy landscape as we can. So I'm just going to say a few words about initially why structure prediction is hard. Eventually it's difficult. Okay, and then I'm going to say some words about why actually it wasn't as difficult as we thought it was for modest-sized systems. Okay, so why is structure prediction hard? Well, it's basically hard because of the curse of dimensionality. So if you consider, let's just consider collections of atoms. If we have a single atom and we need to locate it in the universe, we could just write down 3 numbers and that pins it down in the universe. If we have 2 atoms, then if we're ignoring symmetries and so on, 6 numbers will suffice to pin down those 2 atoms, and then 9 numbers for 3 atoms. Now you can see that as you've gone from 1 atom to 3 atoms, you've gone from a 3-dimensional configuration space to a 9-dimensional configuration space. And these configuration spaces grow extremely rapidly with the dimension. So if we take any random given distance, some sort of length scale, then the volume of the space you have to explore goes as a length scale to the power of the dimension. And the dimension is growing with the number of atoms that you have. So a straight brute force enumeration of every part of the energy landscape becomes rapidly inaccessible. There are not enough clock cycles on computers and seconds in the universe to do those calculations. So this is why fundamentally structure prediction is difficult, because as you increase the number of atoms, going from say a couple of atoms in a water, 3 atoms in a water molecule, all the way up to tens of thousands of atoms in a protein, your space of possible configurations has exponentially exploded. And so this is called the curse of dimensionality. So if you're going to have any hope to make progress here, you're going to have to either use some tricks or rely on some specificities of the particular problem that you're exploring. So I'm going to just take a little bit of a side step here and show you another example, which is in principle pretty difficult. So there's a very famous problem in global optimization called the traveling salesman problem. And the goal there is to take a selection of cities. So here I've got 50 dots spread out in space. And the goal is to find the shortest path joining all those dots in a closed loop. Now, for just 50 dots, there are 50, or this, I know there's 51 dots here. So for 51 dots, there are 50 factorial different paths that you could choose. And that is something like 3 times 10 to the 64. Now, just for context, the number of seconds in the universe is 4 times 10 to the 17. Now, it's very easy to add numbers to exponentials, but it really means something very significant each time you go up an order of magnitude. So you would have to have, if you wanted to, just for this 50-point traveling salesman problem, if you wanted to enumerate all possibilities and check which one is the shortest, you would be having to compute each of the lengths in a tiny fraction of a second, which even modern computers can't achieve. However, I can write down this is the shortest path for that collection of atoms, and I was able to calculate that on my laptop using quite a simple algorithm, really. Okay, so it's gone from being an impossible problem to one that actually pragmatically can be solved. And so this turns out to be a feature of a lot of problems. A lot of problems are formally really, if you wanted to absolutely prove that you've found every possibility, formally difficult and take a lot of computation, but practically can be solved relatively straightforwardly. And so here's some data. This data here, I plotted this myself, but the data was available on this benchmark website for traveling salesman problems, which was a collection of data for how long it was taking to solve particular traveling salesman problems as the number of nodes or points or cities increased. And so we go down from 10 to 10,000 from log. So it's log base 10 of the number of nodes. So when it's 1, it's 10, and when it's 4, it's 10,000. And then I plotted against the log of the number of seconds that it's taken to solve the problem. And for up to 10,000 cities, this is exhibiting quite close to a linear relationship. Yeah, so this problem is behaving at least in a polynomial in a polynomial way. It's not getting exponentially harder practically. And so what is suggested actually is that for an arbitrary traveling salesman problem, indeed that problem scales very more difficultly. But if you take a sort of average typical problem, they can be solved much more quickly. And the kinds of algorithms that are used to solve these traveling salesman problems quickly are shown on the right-hand side. And the basic strategy is you start with a reasonable guess to start with. Then you do something that progressively improves your guess. So in the case of the traveling salesman problem, there are moves by which you swap the links between the cities and check whether the distance has got shorter. And if it has, you greedily accept those shortenings. And you can either do pairs or you can do more complex combinations of cities. You keep doing that until your path can't get any shorter anymore. Okay? And then potentially, if you can't get it any shorter anymore, you just start again with another random guess and then apply the same downhill approach. Or there are other algorithms that maybe, for example, more like evolutionary algorithms that try to do bigger, more global rearrangements of your path. But the simplest thing is start with a random path, improve the path step by step, and then do it lots of times and see what the shortest answer was. And that's basically the algorithms that are being used here with some additional sophistication. Now, you'll see the reason why I've been mentioning this as I go on to the next stages, because effectively that's the algorithm I use for structure prediction. Okay, so I just want to say a few things about the particular problem we're trying to solve. So even if global optimization is in general a difficult problem, potentially in our particular problem, there may be sensible ways of doing okay, of getting reasonably good solutions quickly. And one of the observations for atoms moving around in space, interacting with each other, is that they're interacting through basically Coulomb's law, through Schrodinger's equation, which controls the smoothness of the wave functions. These are all quite smooth interactions. So the interaction between atoms don't suddenly turn on and turn off. They're not sudden little chinks in the energy landscape. They smoothly evolve. Now, that degree of smoothness depends on the particular bonding situation. So if you have a metal that is interacting through a non-directional metallic bond, that energy landscape is rather smooth. If you have a covalent system such as diamond, well, actually bonds are turning on and off in terms of the covalent bonds, and it's a much rougher landscape. And so this would allow you to predict that structure prediction for carbon would be more difficult than structure prediction in aluminium, and that's definitely the case. Okay, these are two sort of extremes, but they're all slightly easier than they would be if the energy landscape was sort of arbitrarily rough. It's not arbitrarily rough. So there's some nice features of smooth landscape. So if your landscape is smooth, and here's an example of a one-dimensional smooth landscape, then there's a correlation between the size of the basin and the depth of the basin. Because what smooth means is that the gradient in the energy landscape is bounded. Okay, there's a maximum steepness that you get in your energy landscape. And so in order to get deep, if your gradient is bounded, you have to travel a long distance with that gradient. And so traveling a long distance with that in a basin means the basin is large. So it's been well observed that computationally that smooth landscapes have this correlation between basin width and basin depth. Now, it doesn't mean the widest basin is the deepest basin. It's just a general correlation. So this suggests a simple sort of sampling algorithm in this case, where we just drop a ball in at random into this energy landscape and roll it down to the bottom of the minimum. In this case, it would be trivial. It would only take a couple of attempts to locate the ground state. So this kind of discussions about energy landscapes are described in a very famous book by David Wales. He's a Cambridge professor of chemistry, and it's sort of one of the sort of fundamental principles of energy landscapes. Now that's good. So that's telling you that the deep basins, which are the ones you want to hit to get the low energy structures, are going to be big, and so should be easy to find. But there's another issue as well, is that what you need to know is what the distribution of basin sizes are. Because if every basin in the energy landscape was the same size, for example, an egg box energy landscape that is sometimes used for testing global optimization algorithms, if every basin is the same size, then the fact that big basins are deep basins doesn't help you at all. They're all the same size. So for it to be helpful, you need there to be big basins and small basins that are taking up different amounts of the overall configuration space. Now, so the question we want to ask is, what is the distribution in basin sizes? There's an average basin size, but what is the distribution? And normally in science, our first guess of what a distribution might look like would be a Gaussian or a normal distribution. And so there'd be an average basin size, and then there's a standard deviation of slightly bigger ones and slightly smaller ones. And this is an example. I've shown an example here of a sort of cartoon of an energy landscape with spheres representing basin sizes. And so this landscape here has a normal distribution of basin sizes. Now, if that were the case, then structural prediction would be very, very difficult. And indeed, this does become the case kind of when you get to large systems. And the reason for that is that if there is a Gaussian distribution of basin sizes, it's equivalent to saying that every basin is about the same. Yeah, there's an average size for the basins, and you can get some a little bit bigger and some a little bit smaller, but not much bigger or smaller. That's the nature of the normal distribution. But luckily, it turns out that's not the case, because this would make it very difficult to do global optimization. So indeed, there's a suggestion, and this is work done by Jonathan Doy and Claire Mazin back in the early or the mid 2000s, where they likened the structure of an energy landscape to be like a fractal. And this particular kind of fractal that they were suggesting it looks like is this thing here called an Apollonian gasket, where you have spheres inside spheres. And so what you have is an Apollonian gasket. It doesn't look, they're not saying the energy landscape looks exactly like this, but it's kind of a cartoon way of looking at it. So you take a big circle, and then you fill that big circle with slightly smaller circles, and then you fill the gaps between it by slightly smaller circles all the way down. So what this means is that there are a few big circles and infinitely more teeny ones, tiny ones, but those tiny ones overall don't dominate the overall space of the configuration space. They take up a relatively small fraction of the whole configuration space. A lot of the, in this case, in this two-dimensional case, a lot of the space is taken up by the three biggest basins. So the distribution of basins in a fractal would actually look more like what we have on the right-hand side, which is a log-log distribution with a straight line, which is a power law distribution. And fractals and power laws are intimately related. And what a power law is saying is, rather than there being an average basin and some a bit smaller and some a bit bigger, as in a normal distribution, it's saying that every size of basin is represented. And the big basins are taking up quite a lot of the space. So what this is suggesting is that this simple algorithm that I've been using and developing for quite a long time, of stochastically sampling initial conditions of structures and then doing local optimizations to nearby local minima, has a reasonable chance of finding those big minima, or those big basins, and getting into fairly low energy structures. And so that's the sort of fundamentals behind Aberdeenshire random structure searching. It gets, and if I've got time at the end, I'll show it. You know, eventually it runs out of steam as you have more and more atoms. Just the number of possibilities become too large, and eventually you can't do this computationally anymore. We've gained a bit of an advantage with machine learning, but still, you know, at some point, you know, you can't imagine if you put the atoms that would make up a mouse, you know, an animal, a small animal, in a computational simulation, and expected it would arrange itself into a living simulation of a mouse. It's not going to happen. The numbers involved are too large. The number of configurations are too large. So let's focus our mind here for structure prediction for modest numbers of atoms, 10, 20, maybe 100 atoms in a simulation. And so this is what we do. But the key thing that made this possible when I started doing this in the sort of mid 2000s was the coming on the scene of multi-core computers. So there was a democratization of parallel computing. And so instead of just doing one or two calculations, which was how things were when I was starting my PhD, we could now do tens, hundreds, or thousands of calculations. And that's how this algorithm works. We start with a random configuration. We do a local optimization, moving the atoms using the forces, moving the shapes of the unit cell if it's a crystal, using stresses. But the key thing is we do it many, many, many times to saturate and sample that energy landscape. So just to make it a bit more concrete, I'm going to show you here a couple of examples. So this is an example for gamma boron, where we take a fixed shape of unit cell. It's an example in the Air software, and at the end I'll show a link to this open source software. We take a fixed shape box, we put 28 boron atoms into that box, and we repeatedly do a structural optimization using CASTEP or a plane wave DFT code, and then record the energies of the local minima, and then on the right hand side we construct a histogram or a density of states of those structures. Now most of the time you end up somewhere in this peak of this distribution, and this is the example I'm going to show the first time. We're starting from a random structure and we're relaxing it, going downhill, and eventually it still looks rather random, and it's ended up here about 0.4 EV above the ground state structure. But about 1 in 100 or 1 in 200 times, we end up down here at the bottom at the ground state. So I'll show you what that looks like. So we start from a random arrangement of atoms, we relax, and we go downhill, 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 and then eventually clicks into this beautiful high symmetry configuration. So there was no symmetry applied at the start. It's found the symmetry. But if you only did this calculation once, you'll likely end up in this big peak up here, which the results look quite random. You have to do this multiple times. It's a high throughput style of computing where you're multiply sampling these energy landscapes. So some features of random structure searching are the following. So there are different approaches to global optimization, and random sampling is one of them. But there are others more based on learning or taking things from previous calculations and using that to make better guesses for what the minima should be the next time round. And so that is those kind of learning algorithms, such as evolutionary algorithms of particle swarms, are used by some people. But I favor this random structure searching, and really these are just different aspects of global optimization. and they rely on the exploration-exploitation balance. So an exploration balance means trying lots of new things. An exploitation balance means trying to learn from previous ones. So learning algorithms, evolutionary algorithms are on the exploitation side, and then random structure search is on the exploration side. Now, I'm a physicist. I want to discover new things. In fact, all scientists should be wanting to discover new things. So I'm not really interested in an algorithm that finds, say, the diamond structure the quickest. I want an algorithm that I can leave running for a week and has a reasonable chance of finding some exciting new material which would lead to a publication and maybe even some application. And so that's why I'm heavily on the exploration side. And the random sampling, we don't try the average, we try the extremes of the distribution. So it's a uniform distribution of initial configurations. Another very strong feature of random sampling is it's intrinsically parallel. So it can be broken up into independent calculations and run on a cloud of computers that are not necessarily communicating with each other very strongly. So it's a trivially parallelizable problem. This means it scales up to very large computing systems. And I think this is becoming more important now as these large computers are becoming available, as the exascale emerges. You can sidestep some of the problems of parallelizing across an entire exascale computer. Other advantages are that each run is uncorrelated, so it means each sample is separate to every other sample because the initial conditions are randomly selected. And this means that if you repeatedly find the same structure, it's telling you something about how well saturated your search is. You're starting to fill out all the basins in your energy landscape because you're finding the same structures again and again and again. Put in another way, if you don't find the structures multiple times, then that's telling you that you shouldn't stop searching. If your best structure, you're tempted to publish a paper on this structure, but you've only found it once, I would say no, keep going. You have to keep going until you found that structure multiple times. Another advantage of random structure searching is there are very few parameters, and so it's rather robust. Once you set it running, you can have confidence that it's going to do a reasonable job, or at least within the bounds of the initial structures that you're choosing. And it's also easy to describe as a method. It's not a complicated algorithm. It's easy to describe in a paragraph in a paper to explain what you're doing. Now, one detail is that when we're making these random structures, they're not, in the some sense, completely random. Now, completely random doesn't really make sense because you always have to draw from some distribution. Okay, so when you're making a random structure for a crystal structure, the first thing you'll realize is you have to draw from a distribution of unit cell volume sizes. Are the lattice vectors in angstroms, kilometers, or light years? Well, they're going to be in angstroms. So we choose from a distribution that goes over a range of angstroms and doesn't have very, very large unit cells. If the unit cell was very large, the atoms would never find each other. You just have a gas or a very, very, very dilute interstellar environment in the light years case. But we want the condensed matter. So we choose the volumes of the unit cells so the atoms are close to each other, but not on top of each other. It's not a good idea to put atoms exactly on top of each other. So actually what we're doing is sampling something called a Poisson disk distribution, where it's disks that don't overlap with it. Then other things you can do to make the initial random structures sensible are impose, for example, chemical ideas, such as the existence of molecules. So if you're trying to find new phases of water ice, then rather than putting hydrogen and oxygen randomly in your unit cell, you can put H2O molecules. You can do some of the work for the algorithm in the way that you're building the molecules first, and then allow those molecules to arrange themselves into other configurations. And you can, in the solid state concept, molecules could be fragments of crystal structures. It's also it can be very useful to enforce different distances between different pairs of species to capture, say, for example, in sodium chloride, that sodium doesn't want to be next to sodium, but it doesn't want to be next to chlorine. You can impose those distance constraints, and you get a lot of chemistry already hard baked into your structures, your sensible structures. It's also very powerful to use symmetry to accelerate the searches. Most crystal structures have at least some symmetry, and if you use symmetry operators, you shrink the configuration space. And given the potentially exponential growth in the size of the configuration space, even halving or dividing by 4 the number of atoms that you have to independently consider can make a huge difference. And then another very useful constraint is to team up with an experimentalist and use constraints from experiment. So for example, experimentalists might know the shape of the unit cell. They've done an experiment, they've done powder X-ray diffraction, they've indexed the unit cell, so they know the shape of the unit cell, but they don't know where the atoms are in it. That's brilliant. We'll do all our searches with fixed shape unit cells, just like I showed you in the boron example. This is very powerful. Okay, so now just to say, this is the sort of first principles versus empirical trade-off. And I'm showing an example on the left-hand side of what happens if you do random structure searching using density functional theory and empirical potentials, such as the Tursoff, very famous Tursoff potential for silicon. And I've done exactly the same. I've got 8 atoms of silicon. I've used the same input files for my random structure searching calculations. And then I've done it with density functional theory, giving rise to the density of structure states in white, and then the Tursoff potential in gray. And you can see that these densities of states are different. Because the density of states are different, and we've done the same sampling, that's saying that the energy landscapes are different. So the energy landscape for the Tursoff potential is not the same as the DFT one. It may be that the Tursoff potential describes silicon well near the bottom of the energy landscape, but it's not describing the whole energy landscape. And for random structure searching, we need to describe the whole energy landscape. So this failure of the Tursoff potential to describe the whole energy landscape would mean that actually random sampling would fail. You'll spend most of your time in the peak of the distribution here, which are made up structures. They're not real silicon structures. Okay, they're false structures. They don't appear in a DFT search. And the probability, there is a small probability, but it's a very small probability of arriving in the diamond structure. Whereas in the case of the DFT, there's quite a reasonable probability of arriving in the diamond structure. So actually, this challenge of having empirical or fast empirical potentials that describe the whole energy landscape was confronted in work I did with Gabor Chani and Volker Deringer in Cambridge, where we actually started to use these developing machine learning approaches to mapping out energy landscapes, machine learning potentials, to train potentials to describe whole energy landscapes in an iterative way. So we make a potential, and then we do random structure searching with it, and if it finds crazy structures, we calculate the DFT energy of those crazy structures, and we put that back into the training set of the machine learning potential. We did this initially for this boron example. Now I'm going to tell you a lot more about that later on. So now I'm going to sort of whiz through a few applications, and then I'm going to tell you about sort of new methods that we're developing in the group. So one of the very early applications of these structure predictions were to high pressure physics. And this was a very fruitful area to work in because these experiments are really rather difficult to do, and relatively little is known about the structure of materials under high pressure compared to the amount that's known under ambient conditions, because there's a whole crystal chemistry and inorganic chemistry and mineralogy, which tells you what the structures are. So this was a prime area for a technique that could predict structures to make an impact, and indeed it did. Both the work of my group, Artem Oganov, Yangwing Ma, were when we first developed these structure searching methods. We were having a lot of fun in the high pressure field of discovering new things computationally, and in many cases them being quite quickly afterwards confirmed experimentally. So here's sort of an example of what we did. So the first, this is work from my group, not so much focusing on the others. So the first application of AIRS, in fact, in this paper of random structure searching, in fact, this was the paper where we introduced random structure searching as a paragraph as a means to an end of what we were doing. We're trying to identify superconducting hydrides. So Neil Ashcroft has suggested that if you mix something with hydrogen, you could trick hydrogen into becoming a metal, and it might be a high temperature superconductor. And he'd made some suggestions with Roel Hoffman of what the structures should be. And then I came along with random structure searches and showed that his suggestions were not correct, in that I could easily find more stable structures. For example, the one here that actually was a semiconductor and couldn't be a superconductor. So this was the sort of first iteration, and we'll come back to this later on, of these structure prediction techniques playing a role in trying to discover novel superconductors. But we also applied it to other areas, to hydrogen at high pressure, ammonia at high pressure. We found that ammonia at high pressure spontaneously ionizes into ammonium amide around 50 GPa. And we also found that at terapascal pressures, the simple metal aluminium becomes quite complex, and it becomes a complex host guest phase. Now, all of these applications in the early years, the first 5 years, say, of doing these structure predictions, I would say were quite simple. We tended to pick an element or a binary compound, and we tended to focus on a single composition and then mapped out the energy landscapes for that single composition. And it led to very many interesting things. But that's not what we're doing now. What we're doing now is we're doing broad explorations over chemical space when we're doing these random structure searching. I almost never do a search at a single composition now. It's already always across a compositional space. So here's an example of that. This is work I did with Andreas Herman in Edinburgh and Lewis Conway, who's now a postdoc in my group, where we explored the ternary chemical space of hydrogen, carbon, nitrogen, oxygen at 500 gigapascals, which is a pressure that's relevant for the planet Uranus. So we were looking at a synthetic Uranus. What would be the effectively organic chemistry that you would see if you were deep inside Uranus? And we sampled a vast number of different compositions. The points on this ternary plot here are only the ones that are stable or close to stable across the convex hull. There are many other compositions that were not even close to stable that we don't see here, but had to be computed to check that they weren't stable. So this search involved hundreds of thousands of generations of structures, a wide variety of different compositions in the hydrogen, carbon, nitrogen, oxygen space. So this is kind of what we're doing a lot of now. Now, I'm going to talk about a similar example in the search for high temperature superconductors. Now, if we were trying to discover unconventional superconductors, we have a problem because no one has produced, well, there isn't a reliable way of taking a known crystal structure and computing the TC of an unconventional superconductor in any feasible time. So we can't close this loop of computing new structures and then checking the superconducting transition temperature, and if it's high, going off to an experimentalist and saying, make that. But we have a different situation in the case of conventional superconductors. And this is, as I mentioned before, very much inspired by Neil Ashcroft, his proposal that metallic hydrogen or doped metallic hydrogen with some other elements might be high temperature superconductors, all starting with silane. So we have this situation we're using certain codes, particularly the quantum espresso code, which has become specialized in this area. For a given structure, we can compute the conventional superconducting transition temperature, and it's reasonably accurate. There are many examples of giving good agreement with experimental results. So now you can imagine a workflow by which you discover computationally new structures using first principle structure prediction, and then if the structure is metallic and relatively stable, you can then compute the TC and see whether it's a superconductor or not. And if you repeat this enough, maybe you'll discover some new candidates, and if you've got some good candidates, you might then be able to convince an experimentalist to go and do that. Now, indeed, this has kind of been happening. So in the field of superconductivity, there's been a lot of excitement around the high pressure hydrides, in that we've broken quite conclusively the highest superconducting transition temperatures that were found for the cuprates. Indeed, the cuprates' highest temperature superconducting transition pressure was at 30 gigapascals. So pressure was already being used to increase superconducting transition temperatures. But these two experimental results here, in both cases, were preceded by calculations of the TC. So these materials were hypothesized using first principle structure prediction. Not always in my group. In many groups have been working on this, particularly a group of Yangming Ma and Daifang Duan in Jilin University. But both these structures were first seen on a computer before they were seen in an experiment. And this is quite a change in the way that superconductivity research has been carried out. And so I wrote a review of, if people are interested in this, it might be interesting to read a review of this. It was 2019. The field's a fast moving field, so things have happened since then that are not covered by that review, but it gives the general idea of this sort of trinity of first principles structure prediction, first principles prediction of superconducting transition temperature through the electron phonon conventional mechanism, and then experiment to confirm those results. And this is a very virtuous loop that we've gone through. And these authors, myself, Ion Eria, who's an expert in superconductivity calculation, and Mikhail Eremets, who's an expert in experiment. And it really reflects this trinity, this grouping together of three approaches. So what have I been doing more recently? Well, this is an outcome of a paper we published in 2021, which was a collaboration with 2 PhD students in the Cavendish Laboratory in Cambridge. And so what we decided to do was to, so random structure searching itself is a kind of high throughput calculation. We take lots of structures and we calculate DFT for them. But we decided to go another level up where we high throughputed the high throughput calculation. So instead of calculating the stable structures for a given compositional space, we actually searched through a whole range of compositional spaces, and in this case, through the whole range of binary hydride compounds. So at a series of pressures, I did a high throughput random structure search for high symmetry small unit cell binary hydride. So it's always hydrogen plus another element from the periodic table. We compute the structures, we identify which ones are metallic, we identify which ones are quite close to the convex hull, relatively stable, and then actually we used a simple machine learning model to guess whether that structure was likely to be a high temperature superconductor, and if it was, we then went on and did the calculation of the high temperature of the superconductivity from first principles. And so there's this sort of triage approach where maybe we're finding 100,000 structures in a search, and then we reduce that number to something like 1,000 structures by considerations of stability and metallicity, and then the machine learning model will pick out maybe 20 or 30 of those structures to calculate TC for. And here are the results for that. On the right hand side you've got a table, and every one of those structures which is underlined was for the first time computed as a superconductor in our paper. We obviously rediscovered quite a lot that had been studied before by other people, and those are not underlined. But we found quite a lot of new ones, quite a lot of new high temperature superconductors, potential high temperature superconductors in our searches. And then we plotted them on the left hand side on this curve, which for me, the red dots are the results from our work, the green dots are experiment. You can see that there's this CSH result here. This was a result that was published actually in Nature in 2020, but has subsequently been retracted. So we're not really quite sure what the status of that is at the moment, but the lanthanum and sulfur hydride results are fairly solid. And what we see here, what I find most interesting, is that yes, as you go to higher and higher pressure, you can find higher and higher TC candidates. So one of the ones we had here at 500 GPa was way above room temperature. But as we decrease the pressure, actually the TC was not dropping that quickly, suggesting that, yeah, well, maybe room temperature superconductivity ambient conditions might be challenging, but having something around 200 GPa, 200 Kelvin might be very feasible, and this would be a nice target to find. Okay, I think I'm gonna go through this section very quickly, really just to show some pictures. But I'm not going to go into the details of this. If you're interested, you can look up these techniques yourself, and I'll show a reference of a paper that we've written. But what this is about is a way of, when we're doing these very high throughput calculations and we're generating hundreds of thousands of structures in our searches, it becomes very difficult to manage and visualize the data. So we spent a bit of time looking into actually machine learning inspired techniques to do dimensionality reduction of our data space, so we can actually plot our data on a page and have a look at it and see how it's behaving. And so the particular technique that we got invested in is manifold learning, and the idea behind that is that your structure maybe be turned into a vector, a feature vector, or a descriptor. This is a standard step in machine learning, where you have a three-dimensional structure and you have to turn it into some sort of vector so you can do machine learning on it. So let's not worry about how exactly that's done, but that's a crucial step. But each of those vectors live in a very high dimensional space, and maybe you have hundreds of thousands of those points in that high dimensional space. So what you need to be able to imagine is that you're maybe in a 1,000-dimensional space with points in that 1,000-dimensional space, and each one of those points is a structure. And obviously you haven't got a computer screen or any piece of paper that can look at 100-dimensional objects or 1,000-dimensional objects, so you want to reduce that dimension down to 2 or 3 dimensions so you can look at it. And what manifold learning does is it makes a hypothesis that data actually lives on a lower dimensional manifold or subsurface in that high dimensional space. And if we can identify what that manifold is, we can take that manifold and unfold it down into our lower dimensional space. And that's what I'm showing here, is we've got this, say, a Swiss roll or rolled up manifold in a higher dimensional space that we then unfold into two-dimensional space. And that's the basic idea. Now, I'm not going to go into the details here. We developed a particular algorithm which was based on previously known ones, and we tuned it to be advantageous for our particular application. And I think this is an example applying it to a standard machine learning application. Our method is SHEEP. The previously known ones are TSNE and UMAP. And our method seems to do really rather a good job of doing a dimensional reduction of handwritten characters. This is a classic task in machine learning. Obviously, we're not interested in handwritten characters in our research, but we thought we'd better test it against the current state of the art, and it certainly behaves. UMAP is considered a good one by the machine learning community, and I think ours is probably maybe even slightly better than that. It's definitely better at separating things than the TSNE. So we apply these algorithms now to data sets of structures, and one example here is the Lennard-Jones clusters. So we take a Lennard-Jones 38 cluster. It's a known challenging cluster for global structural optimization, and we apply this manifold learning algorithm to it. So each one of these dots on this plot is a structure, or in fact, some of the dots are bigger than others. That maybe means that there's been multiple copies of structures. So each dot is proportional to the number of copies of structures that we have in the data set. And so there's about 100,000 points here. And then when we do this manifold learning dimensionality reduction, which is published in this PRX paper in 2021, you see all the nice features of the funnels and structure of this energy landscape. And this is very nice. So this is not something you can visualize if you're just staring at lists of numbers. But with this algorithm, features emerge. You start to be able to query your data. You start to learn more about it. And so we're now using this often in our research. One of the results here is using it to map a structure optimization. So we've got the colorful points here is a dimensional reduction of a set of Lennard-Jones 13 clusters. And what we're following here is the geometry of evolution of a Lennard-Jones 13 cluster as it passes through that energy landscape and eventually ends up in the ground state structure. So you can have a look you can visualize geometry optimization in this way, which is something a little bit hard to do otherwise. One striking feature we found was that actually 3 dimensions was enough. We couldn't get any improvement by going beyond 3 dimensions for these data sets, which is good because we can only visualize 3 dimensions ourselves. So here's a 3-dimensional dimensional reduction of that Lennard-Jones 38 structure. And you can see it's rather similar at certain orientations to the 2-dimensional one. 2-dimensional was pretty good. 3-dimensional basically don't get any better when you go to 4-dimensional. This is kind of interesting. This is telling you that these structures are indeed lying on a low dimensional manifold. There's nothing really more in the structure than 3, say, dimensions worth of 3 dimensions worth of structure. This is actually quite relevant for machine learning. It's telling you that there is this simplicity in the higher dimensional space that a machine learning method might be able to exploit. For example, for generating new structures, generative AI may find this manifold, and if you could navigate this manifold, you would end up with many structures that are close to the ground, close to the local minimum, as opposed to being random structures. So we've also applied this to another carbon, hydrogen, nitrogen, oxygen system, this time at 0 pressure, and it's just very useful. It's very useful. You can map out organic chemistry in this way. You've gone from water to graphite to carbon dioxide and various other things, carbamic acid. I mean, there's probably, if you were an organic chemist, you'd probably be able to give a name to every one of these spots in here. We're physicists, so we're not able to do that, but we found a few of them. Now, so just to finish off, I'm going to give a whistle-stop tour to what we're doing in my research group now. And this is pretty much entirely moving our research from doing fully first principles structure search to doing a machine learning accelerated structure search. We're really at the point now that we very rarely do first principles geometry optimization. i.e. we moving atoms using first principles forces. What we would tend to do now is we would use a machine learning potential to quickly move the atoms to the low energy configurations, and then maybe refine it using DFT at the end of the search. And this leads to a massive acceleration of our workflow, and is enabling us to do things that we couldn't do before. And so this all comes from a project I actually had. It was kind of my COVID project when I was sat at home, when I wasn't giving lectures online. I was playing around with trying to get to grips with machine learning. And in the process of that, I developed these machine learning potentials, which I called ephemeral data-derived potentials for random structure search. So the idea is, of course, there are many other research groups that are working on this. Almost every research group has their own machine learning potential. I decided to make one which was just right for my task. Every design choice I was making is entirely focused on random structure search, not molecular dynamics, not anything, not reaction kinetics or anything else. I'm just focusing on navigating the energy landscape because that's what I like doing, structure search, and so I want to make that faster. By doing that, you can make choices that are different to what other groups would make, and then maybe end up with something that's particularly effective. And so the idea, I call these potentials ephemeral potentials because I've tried to make them easy enough to generate that you would do them in the course of doing a structure search, and maybe you'd make 20 potentials a day. You don't just do one PhD making one potential for one chemical system. You're actually doing it just as part of your everyday workflow. And so they're ephemeral, suggesting that you throw them away and make another one if you want to. Okay. And so the idea is you would make a potential that is designed for the particular subspace of configuration space that you're exploring in your search. And the idea was inspired by observations I'd made actually with a PhD student in UCL, Martin Urin, where we had noticed that much of binary crystal structures could be described by simple binary Lennard-Jones style potentials. So if you make a binary Lennard-Jones potential with random A and B parameters, allowing the B to be negative as well as positive, and then you did a random structure search using that potential, you could find certain structure types, and as you did that for different values of A's and B's, you could map out a whole range of different possible structure prototypes. So I knew actually that structure could be described by a very simple potential. But there was a problem. If you had an elemental system, then a simple Lennard-Jones potential can't capture any of the structural richness, say, of graphite or diamond or carbon or boron in general. And this is because three-body terms were important. So I knew I had to go to three bodies. And so I kind of tried to channel the spirit of Lennard-Jones, who came up with this very simple and computationally efficient potential. I tried to write down what would be an equivalently simple potential, but for three-body term. And this is the potential that I came up with, which is basically, if you're sitting on atom I, it depends on the interactions between I and the neighboring potentials, neighboring atoms K and J, and they are interacting through the same way so that you're permutationally equivalent. And then also we have to consider the interaction between the neighboring atoms, which is given another strength of interaction or power of interaction here. And then there's a strength of interaction that we choose. So we have a few parameters that we can adjust. And when I added this potential and then repeated doing the air searching for different values of these potentials, I found even for elemental systems, I could find the diamond structure, the graphite structure. I could also, for certain choices of these parameters, find boron structures, such as the alpha boron structure. Now that's quite a complex structure from such a simple potential, and suggested to me that it was on a good track. And so I took this inspiration, and I'm not going into the massive details of it, but we used this to inspire a functional form for a simple machine learning potential. And so my body interactions are just in terms of two-body. It's a function of the distance raised to some power. A three-body term is a product of functions of distances raised to different powers, and you can generalize it to four-body terms as well. Now, the function I use for Lennard-Jones is 1 over R. I don't use 1 over R because 1 over R is not cut off. It has an infinite range. And that means that your calculations get very expensive because you have to consider very, very large distances, or you have to cut off the potential anyway in some brute way. So what I did instead is I chose a function which was naturally cut off. And it was just a straight line between, say, 2 and 2, passing through 1 at halfway along, raised to different powers. And so it behaves rather like a Lennard-Jones style, a 1 over R as you raise the power, but it's cut off. So once we develop those interactions, we use those to turn them into a descriptor or a vector, which could then be fed into neural networks. And so what I've done is I do a neural network, do a neural network fit, but I fit multiple numbers, like hundreds of neural networks. I make an ensemble of neural networks, and then I combine them together. And I combine them together not in a normal ensembling way of adding them up and dividing by the number of neural networks that I have. I use something called non-negative least squares. And what that means is I enforce that the weight in front of each neural network potential is a small positive number. If you do that and try and fit the potential to a held out data set, you end up with a sparse solution. You either have some neural networks that have no value whatsoever and have a weight of 0, and a handful that have a higher weight. And so that's a way of distilling the hundreds of small neural networks down to just a handful. And this leads to robustness and smoothness, this ensembling of the potentials. As I mentioned before, we use an iterative approach, an active learning approach, where we start by making a potential based on completely random structures, the DFT energy of completely random structures, because we need this potential to work for completely random structures, because we're going to do random structure search. So we have to we want really random structures in the data set, but they're pretty rubbish structures, and we make a potential that is fit to those rubbish structures, and it probably will lead you to a lower energy region of the configuration space, but the structures you get are probably wrong. But then we just feed that back. We go in a loop. We take the minima that we found from the first generation of potentials. We calculate the DFT energies, and then we feed that back into the data set, retrain the potential, and go round in a loop, typically about 5 times. And that's our active learning approach. And that leads to potentials that we can then use to do further random structure searches on, because they've been trained to know how to deal with crazy random structures, and they've also learned how to deal with low energy structures as well. And so they deal with the whole energy landscape. So here's an example of a predicted versus DFT energy curve or plot for, this is a lithium iron oxalate compound. It's a ternary species. It's quite a lot of different elements for machine learning potential. And what you see is really good agreement down at the low energy part of the landscape, with less emphasis on the higher energy part. And the idea here is that even though the overall error in this potential might look quite large because of these large deviations up here, they're in the part of the energy landscape that don't matter very much. You're never going to end up, even in molecular dynamics, like multiple electron volts above the ground state. You're going to be spending all your time down here. But when you're doing random structure searching, you do start up here. So you need it to be roughly right up here, but you need to be really right down there. And this recipe leads to this sort of funneling effect of the accuracy down to lower energies. So here's just another example. This was some work by Si-Hun Ju, one of my postdocs, who's working on using this for searching for new battery cathode materials. This is testing on a very known lithium cobalt oxide. But it shows everything together. We're doing random structure searching, we're making machine learning potentials, and then we're using these manifold learning maps to look at the data as we go along. And this is our modern workflow now in the group, where it's got multiple levels of machine learning that are accelerating and helping our visualization. Now, in this paper I published, the ephemeral data-derived potentials of random structure search, I'm a developer of methods, and I'm constantly developing new methods. On my hard drive, I've got loads of new methods, but I don't publish very many of them unless they prove to be considerably better than what's in the literature, or enables people to do something that they wouldn't be able to do. It's probably not a good idea to confuse people with lots of new methods. And so I sort of set myself a task when I'm developing a new method that I have to show in the methods paper an example of it doing something that couldn't be done before. And so for this paper, I took the example of going back to my original silane work and just seeing what would happen if I used machine learning potentials to do that search now. And what I discovered was a much more complex structure than I published, than other people who worked in this area had published over the years. And indeed, this structure on the left-hand side has 60 atoms in the primitive cell. And it's the red curve on this plot here for the enthalpy, and it's just much more stable than any others. It knocks all the other structures out of the water at higher and higher pressures. So for me, this tells me a couple of things. One, these machine learning potentials are enabling us to do things we certainly hadn't done before. Maybe we could if we knew the answer now, but we didn't. So it's enabling new science. It also is probably telling us that we probably haven't finished our search in the binary hydrides. The binary hydrides or even ternary hydrides are probably more complex than people in the literature suspect at the moment. So we are, in our research group, we're revisiting the binary hydrides. Now, why did I go to all the effort of making my own machine learning potential? Maybe I could have borrowed someone else's. Well, I had, as I mentioned, I'd worked with people using machine learning potentials, and my feeling was when I was doing random search, now it got better over the years, but even so, when you're doing random search, it's a very good way of breaking a machine learning potential and sending the structure into an area of configuration space where the potential hasn't been trained. How this manifests itself in machine learning potentials is that you have regions of the energy landscape where the potential is well trained, particularly around the region where you've got a lot of data. But in other areas, it might give spurious results. And this has been sort of made clear by a plot made by Ralph Droutz and his group for carbon, where what he did, he's been developing these ACE potentials, which are really rather nice and smooth. But what he's done is he's taken various polymorphs of carbon and then varied the lattice parameter for those crystals. So scanned the lattice parameters and observed the energy landscape in these different structures. And for his ACE potentials, it's nice and smooth. But for various other carbon potentials that are well used in the literature, all kinds of crazy things happen. This would not be very good for structure searching, because unless you're in the area at the bottom, this is where these potentials were largely trained, I guess. Down here, where you can tell the difference between graphite, diamond, and graphene. That's all good. But for these other phases, there's all kinds of other things going on. And this would be a bit like the Tursoff potential issue that I had. Lots and lots of configurations which were not so meaningful. So this is what we just put a paper on arXiv, sort of revisiting the EDDP, the ephemeral data derived potentials. And in that, we examined the smoothness of our carbon potential. And actually, our simple algorithm comes up with a nice smooth potential. It explains why it's appropriate for structure search. The energies aren't perfect, but we didn't tune it to make the energies perfect. We just really want to get the structures roughly correctly. So this is a sort of post-justification of, oh yes, that's why these ephemeral data-derived potentials, with all the ensembling, the simplicity of the functional form, it drives you towards a smooth potential. So here's some applications. I'm just going to show you a few applications. So this is to the lead phase diagram. This is work done by Pascal Salzbrenner for his PhD. Lead is a heavy element. Strictly, it requires spin-orbit coupling to give a good description. And being a metal, it needs a good description of the Fermi surface. And this requires a high K-point sampling. So if you wanted to know what is the melting point of lead from first principles, you will not find very many first principles ab initio molecular dynamics coexistence melting simulations of lead, because the computation expense is so great. So what Pascal did is he trained a very accurate potential, so very accurate DFT calculations for small unit cell structures of random structures in the iterative way that I've just described, and then use that potential to do large-scale molecular dynamics simulations to map out the melting line, as well as different phase transition lines for lead. And for me, it's really striking how close, especially once you include the spin-orbit coupling, how close to the experimental observations we are. We're a little bit off on the FCC HCP phase boundary, but it's a fraction. It's less than a GPa, a gigapascal difference. So for me, this is really striking. We can use these potentials to tackle systems that would just be computationally out of reach using first principles method. And to put some numbers on that, Pascal estimated if you're using DFT for 8 atoms of spin orbit coupling lead, you could generate 0.0004 structures per core hour, okay, using DFT. Whereas for the EDDP, you'll generate 37. And so you're like, I don't know, how many is that? 10,000, 100,000 speed up. These are multiple orders of magnitude that the machine learning is giving us. This is game changing. It allows us to do things that we didn't do otherwise. So an example of that is metal organic frameworks. So Lewis Conway, I mentioned who's in my group as a postdoc, built an EDDP potential to describe the zinc cyanide MOF structure, or actually just the zinc cyanide chemical system, and used that to he used random structure searching to generate a whole collection of MOF structures. He was able to identify that he'd found the ones that are considered in the literature, as well as many other MOFs. But then he was able to go a step further and making supercells of these MOFs. He was able to do a molecular dynamics simulation at a range of temperatures and measure the variation in the lattice parameter, and he could actually calculate the negative thermal expansion for these different cages. And for one of them, the dia C, which is an interpenetrating diamond structure, it's this one here. He was able to calculate I think around room temperature, a negative thermal expansion that numerically pretty much agreed with experiment. Now, this could be accidental or coincidental. So I asked him whether he could do a DFT simulation to check that one result. He doesn't have to do everything, just that one result. And unfortunately, he's tried and he's come back and he can't even do the DFT calculation. Now, this is using maybe in the US you have big enough supercomputers, but in the UK our supercomputers are not big enough to do that calculation. And actually, this is quite interesting. It's leading us into a sort of a new regime where these machine learning potentials, which are no longer entirely first principles, are allowing us to compute properties that we can't always double check using first principles methods. And in principle, that would be the best thing to always do. If you've got a new discovery, double check it with DFT. So this is going to highlight the importance of uncertainty quantification in these machine learning in these machine learning models, because it's going to be very tempting to use these models to make predictions and to support experimental results. But we have to be aware that these machine learning potentials can never be better than the DFT. They're an approximation to that with potentially pathological errors in them. So we have to be very alert as we work in that area. So I'm just going to finish off here with a couple of words. This is literally what we're doing in the group right now. And this is exploiting this maybe 10 orders of magnitude, or not 10, several orders of magnitude acceleration due to molecular dynamics, due to machine learning potentials that are enabling us to do structure search in a different way. So the traditional way of doing structure search is you build a random structure, you do some relaxation, either with DFT or a machine learning potential, and then you store the result, and then you do this multiple times to build up a sampling of your landscape. What we're doing now is we're building a structure, we're relaxing it to the nearby local minima, and then we're running long anneals, molecular dynamic anneals, which is like in metallurgy, you anneal something. You've got a messy structure, you anneal it, you get a neater structure. This is what we're doing. We're running anneals at a temperature, maybe half the melting temperature, a little below the melting temperature for about half a nanosecond, and then we stop, then we relax it, and then we store it. So this is nothing but actually another optimization algorithm. We go downhill, we wobble around on the energy landscape, we go downhill again. The end result is an optimization. It's a little bit like in machine learning. Those of you who know anything about machine learning, for training large neural networks, they use stochastic gradient descent. They use effectively temperature to anneal their parameters in their neural networks. And so we're doing something similar now, which we couldn't do before. You could not do this with density functional theory, because the half nanosecond of MD for every structure you're doing would just burn up your CPU budget. But what happens is something very nice. So here's the result. So if you do normal random structure searching, and this is for a cubic box with 256 silicon atoms in it. If we do a normal random structure search, so we pick a random structure, we go to the nearby local minima, we end up with a distribution that looks like this. Okay, this big red peak. And this is basically the rapidly quenched melt the instantaneously quenched melt of silicon. But it has lots of frustrated bonding. It's not all tetrahedrally bonded. It's not particularly low energy. But however, if you at 900 Kelvin, which is below the melting temperature of silicon, and anneal for 500 picoseconds, you do the same sampling, you end up with this very different distribution. So you end up with some that are similar to the previous fast quench melt. You end up with another peak that, when you look at the structures, consist of almost entirely tetrahedrally bonded silicon. So this is like an amorphous silicon network. And then at lower energy still, you end up with polycrystalline structures. You don't get crystalline silicon because crystalline cubic silicon won't fit into this 256 atom box. So it's frustrated. It's forced to make different domains. And that's what we see on the right, on the left-hand side here, is mixtures of cubic and hexagonal silicon. So this is changing. This is, this is quite new. We're not fully explored the consequences of this. It's a new, new optimization strategy that's become enabled by just the speed of these machine learning of these machine learning potentials. So no major discoveries yet, but it's an interesting use of these of this algorithm. Okay, so I'm done now. So the conclusion is, when we're doing structure search, it searches over compositions, not just structure, that's interesting now to find new chemistry. And then these data-derived potentials, they really do speed things up. And one of the key things is we're starting to be able to put temperature into our searches. And so just to finish off, the code, the DFT code that I'm a developer of, CASTEP, it's not open source, but it's available for free for any academic researcher globally. You just have to go on a web form and sign up for it. So everyone can use that. I use that all the time in my structure searching. But my random structure searching and the machine learning packages, they're open source. You can just download from our website and do whatever you like with them. But if you want to get in touch, we have an email address there. Okay, so I think I've finished now.